Hello and welcome to our series on calculus. This video will serve as a brief introduction to the mathematics of calculus and the motivations behind its development. Now, calculus was developed in order to solve an important problem regarding rates of change. Okay, so calculus is all about describing and analyzing functions and their rates of change. Specifically, though, with regard to curved surfaces or curved functions. Okay, so to get a sense of what I'm talking about, let's start by analyzing a straight line, a nice simple linear equation, okay, like this one here. Y equals 3/4 x, right? So if I plot this, if I plug in 4, I should get 3, right? So I'm going to have the point 4, 3, and it's going to be centered at the origin. So I could just draw a nice, simple, that was a terrible straight line. Let's try that again. There we go. Nice, simple straight line that goes right through that point. And in this case, talking about a rate of change is quite simple, right? So this is my x-axis and my y-axis. The rate of change is every time x goes up by 4, right? You move 4 to the right, y changes by 3. And that proportion is constant throughout the entire function, right? It doesn't change at all. It's just a nice, simple rate of change that is constant throughout, right? So if we added, if we wanted to, we could add concrete meanings to our variables, right? So I could call x time in seconds, say, right? So this would be 2 seconds, 3 seconds, 4 seconds, etc. And y, I can make distance in meters. Okay, now my rate of change has a concrete physical meaning. This object is moving 3 meters every 4 seconds, right? Or every 1 second, it's moving 3/4 of a meter, right? However you want to think about it, that ratio is the same. It's constant, okay? So this is really quite easy to work with. No calculus is necessary here. Another related problem, if I change my y-axis here to velocity, so velocity, remember, is talking about an object's rate of change. Have that in meters per second. Right now, this object's velocity is changing, right? At the beginning, its velocity is 0. Now, 4 seconds later, its velocity would be 3 meters per second, okay? Suppose we want to know how far this object has traveled during this 4 seconds. Well, in this case, the answer is given by the area under this line. This area, which will have units of, notice, meters, right? If I multiply the two dimensions together, I will get, the seconds will cancel, I'll get meters. This area represents the total distance that this object has traveled during this 4-second time period. And in this case also, the answer is easy, right? We have a nice, simple, straightforward formula for the area of a triangle. 1/2 base times height, right? Which would, in this case, would be 1/2 times 4 times 3, right? The base of my triangle is 4, the height is 3. This would give me 6 meters. So during this 4-second interval, this object has traveled a distance of 6 meters. All right. Again, no calculus is necessary here. Okay. Now, the problem arises when we leave the realm of nice linear functions and we enter curved ones. Okay, so now let's consider a different function, and let's go back to thinking about distance for a second instead of velocity. This time, let's consider the function 1/4 x squared. Okay, so this graph is not going to be a nice straight line. I'll just graph it out really quickly here. It'll look something like that, okay? And again, you can see we no longer have a triangle. Now we've got this sort of awkward shape, okay? And it's no longer a straight line, right? What is the velocity of this object? What's its speed, its rate of change, right? If we're thinking of distance versus time here, well, it's not clear, right? You could kind of pretend that this is a triangle and draw this back and just say that it's 3/4 meters per second again, but that's not really a very satisfying answer. A better way to think about it is to say, well, this rate of change, or sorry, this, the rate of change is itself constantly changing, right? The slope of this graph is different at every single point. It is constantly getting, in this case, steeper, right? So a better way to think about this is, well, let's see if we could find the tangent line, the slope of the tangent line at any given point. So say I wanted to know the tangent line here. Remember, a tangent line is just a line that touches at just one point, right? So it kind of gives you an idea of the instantaneous rate of change. That would be the ideal, but this was a very difficult problem to solve, and it's not so, there's really no way to do this just using the mathematics of straight lines, okay? A similar problem, right? Say again that we wanted to know the area under this curve. So, maybe now we're not so interested in just the rate of change per se. We want to know this area. Okay, well, this also is not so easy to do. You might think of ways to approximate it, right? We could have, a series of rectangles that we create, and that's not a very good approximation, right? But it's one idea. Well, we could make this better. Maybe let's double the number of rectangles that we have, right? And then we remove a little bit of the extra space there, right? And you kind of get a sense that the more rectangles we do, the better it'll be. But so long as you're just using a finite number of rectangles, you're only ever going to get an approximation, right? You're never going to get the true area. Okay, so this is the problem that calculus is occupied with. And the solution to both of these problems, the tangent line problem and the area under the curve problem, are solved by the use of something called the limit, which is the foundation of calculus. It's really the underlying principle that undergirds the whole thing. In the next video, we'll get into that, and then in subsequent videos, we'll finally take a look at how these two problems can be solved to get an exact expression for the slope of a tangent line at any point, and the exact area under the curve, for some given interval, right? Before we stop today, I'll just take a moment to mention that the development of calculus represents more than just a revolutionary advancement in mathematics. It also allowed us to develop physics properly. It allowed advancements in chemistry, biology. It even touches some of the social sciences through things like statistics. If you've studied probability and statistics, much of statistics is undergirded by calculus. So if you work in any STEM fields, or even in some of the social sciences, the chances are good that your discipline has been touched by calculus at some point in some way. So if you're wanting to learn more about the mathematics behind calculus, this is the course for you. In the next video, we'll take a look at limits and how they work. Thank you for watching.